system are that everything is safe. There are no exposed moving parts to the students, and we use electrical switches to ensure that. It's all done with 24 volts. That enables us to have a very small control unit, which really lowers our cost. This is less than half the price of any other system on the market, as far as we're aware. You can either use it in a manual mode. Electrical installation people are not comfortable with computers, so that's designed for them. But most of the time, you use it in PC mode with custom software, or you can use it with Matlab or LabVIEW. It's got a full API inside it. The box is for AC and DC machines. All the machines are physically very small. That means it can be put away, it can be packed away, and you don't need a dedicated lab for the study of electrical machines. Here you can see the control box. It's all shrouded 4mm connectors. This is the dynamometer. So basically you can just alter the resistance in the dynamometer. There's about 16 different virtual instruments embedded in the system. Some of them come as part of the experiment itself, but there's a couple of voltmeters and a couple of ammeters that you can use there as well. This is how you control the DC power supply, and here's the 3-phase AC outputs. As I say, there's an API for LabVIEW, and it's small and quite compact. And this box is really a very high-tech box. It's got about 4 different computers inside, all communicating to each other and then back to the computer via local area network or USB. Here you can see some of the machines we have. We have a dynamometer, which is also a DC dynamo, a DC motor, a universal motor, which is either AC or DC, a single-phase induction motor, a 3-phase induction motor, a shunt DC motor, and there's a brushless DC motor. Brushless is really important. It's one of the most important types of motor used in vehicles, for example, and modern industry, because physically it's so much smaller that the power of these things is all about 50 watts. So the power of this DC motor and the power of this brushless motor are the same. And of course, if things are physically smaller, they're cheaper to make, and so on. So brushless DC motors are a really key motor that is going to be used in the future more and more. The software, there are about 3 different software applications that are shipped with the unit, which allows you to carry out all the different experiments. And this is in DC and also in AC. You can do speed torque curves. There's an integrated oscilloscope, which I'll talk more about later. And it's really quite a sophisticated system. The curriculum we've covered. And this is the advanced electrical machines pack, which is what we want to talk about today. Here you can see some images of the worksheet, so you can see the style and design. This is designed for second year university, and at this level, the key thing that students need to do is really to understand the equivalent circuits of electrical machines. And when we're talking about electrical machines, transformers are viewed as an electrical machine, so they don't all have moving parts. When you're looking at this kind of curriculum, you do need some kind of mathematical package, and people often use Matlab, but there is a great free package called GNU Octave, which we've used for doing all of our calculations. And this allows you to do a sequence of calculations and to plot graphs and other stuff like that. This particular pack, the workbook, will take a student about 15 to 20 hours to go through, we feel. There's another pack that goes alongside this, which covers the use of Matlab with electrical machines. What we're talking about today is the characterization of an electrical machine using a circuit. Now, and when you're using Matlab, what you're able to do then is you're able to develop a circuit and then predict how the machine will behave under certain characteristics. And that's one part of how you use Matlab for this. There's another package that you can use which allows you to take that a whole stage further, where you give Matlab control of the box, and then Matlab can take all the measurements you need, and it provides another level of sophistication for customers who want their students to undergo a pretty heavy Matlab course. And that's another 15 to 20 hours in just using Matlab to do that. Okay. I don't want to talk about that, I think. So the learning objectives here in level 5 then are the equivalent circuit of transformers, the equivalent circuit of induction motors, how you gather those terms, how you do the calculations, and then how you build a model using some software. This is mostly undergraduate. We have in the UK, I think there's some UK people listening. This also applies to the BTEC Higher National in Unit 43, where you've also got to do some modelling of electrical machines. The transformers add-on, basically what we're doing is we've just got an iron core here, which is a demountable iron core, and then we're shipping a number of number of coils with a few hundred turns each, which then slot onto that core. So you can build your own transformer, and you can then build quite a few different types of transformers with different ratios of input and output turns. So that's our transformers add-on pack. What we do have, which is useful if you're thinking of purchasing the electrical machines pack, or for some of our partners here who are hoping to sell it, we have a great document which shows you all of the results that can be gathered with the equipment. And you can see some images here of the speed torque curves and the oscillograms and the equivalent circuit measurements. And so if you're interested in how our electrical machine system works, then getting this document will show you the results that you're able to obtain. And of course, that then dictates the different types of learning that can be done with it. And if you want that document, just contact Alistair and he'll give it to you later. So we've covered some of this. We've covered that. So I think when we're starting to look at electrical machines, induction motors, and how they're characterized, very often students start with understanding how a transformer works. And it's interesting that the reason why transformers are considered part of electrical machines is that the mathematical problem of characterizing a transformer is almost identical to the mathematical problem of characterizing an electrical machine. And when we're looking at a transformer, this is a model that we build. And this is the circuit equivalent of a transformer. And there are different types of losses, if you like, in a transformer. And the losses are partly resistive losses in the primary, which is R1, and in the secondary, which is R2. And the energy needed to magnetize the core can also be modeled as a resistor. And we call that the magnetizing resistance and the magnetizing reactance. And so this is an equivalent circuit of a transformer. And these two reactances here are the reactance of the primary and secondary core. And there is a sequence of mathematical steps you can go to start off with a transformer with two separate circuits on the primary and secondary, and then you deduce that actually this is an equivalent circuit of the two. And of course, this is an easier one to quantify because the components are connected together in an electrical circuit. Now, when we're looking at this, we make some engineering assumptions about the relative values of these terms in the circuit, and that allows us to carry out some tests. Now, for example, when there is nothing connected to the secondary, the losses in these two terms here are pretty small, and these terms here are much more significant in the circuit. So we make a really broad sweeping assumption that all of these components become zero, and these are the only components that matter in the circuit. And this is a hard one for students to get to grips with because it's done through experience. In practice, we know that these are the dominant terms. So the first thing we do with the transformer is we carry out an open circuit test and we assume that this is the circuit. Conversely, when we short circuit the secondary winding, we know that the magnetizing losses are relatively small compared to the other losses in the system. So we make an assumption that these goes to zero and the circuit equivalent is shown here. So by carrying out these tests with a transformer, we can deduce the values of the circuit. Now you can see the setup here. The electrical machines box has a single phase output. We put that into the primary side of the transformer. The secondary is open circuit. We're monitoring the voltage there. And then the students are taken through a sequence of calculations so that they can deduce what those values are. Now to do that, they need to understand the phase difference between the voltage and the current in the system. And they do that by using the internal oscilloscope. So we mentioned earlier that there are 16 virtual instruments inside the box, and in the software you can choose which ones of those are displayed on the oscilloscope. And you basically just measure the angle between the two peaks of the two different voltage and current waveforms. And the internal oscilloscope is brilliant for this. It's a really great tool. It's not particularly quick. I don't know what the sampling frequency is, but in terms of displaying that information, it's really, really useful. Now, when you do this, you go through a sequence of calculations, which you can see here. There's just a small amount of trigonometry, and that allows you to deduce the values of XM and RM. And here you can see XM is 52 ohms, RM's 86 ohms. So that's the first part of the problem. The second part of the problem is the short circuit test. It's very similar. The only difference is we short circuit the secondary side. The sequence of calculations is almost identical. And that allows us to, again, come up with a set of values. And we had 80 ohms and about 60 ohms for the magnetizing components. And here you can see that the rest of the components are all under 10 ohms. So our original assumption about the relative values of these things is quite true. So there you can see for the transformer, the values of the components in the system. And for there, I had a very simple transformer with 400 turns on the primary and 600 turns on the secondary. So that's the transformer. Now, when it comes to looking at an induction motor, the equivalent circuit is very, very similar. But there is a second resistor in the circuit you can see here. And this resistor allows for the slip, the mechanical slip in the system. And we can define the value of that resistance as being R2 multiplied by 1 minus the slip over the slip. And again, what we can do, slip is, induction motors never run at the frequency of supply. There is always a slip. So if you give an induction motor a 50 hertz supply, it'll run at 40 hertz or whatever. Now that slip is determined by the load on the system. If there's a greater load, there's a greater amount of slip. And if we look at that value there, we can say that when the machine is free running, the slip is pretty close to the supply frequency, right? So we can assume that I'm going to have to get this right. I'm going to go to the next one before I say that because I'll get it wrong. But basically, if we know what the value of slip is, it allows us to make similar assumptions to the transformer, right? So when we are free running, the slip is 0. So we can assume that the terms in the circuit are limited to the magnetizing components. And so this is free running. So in a free running test, the magnetizing components are far greater than the other components in the system. So just like for the transformer, what we can do is set up a 3-phase supply and we can go through a series of calculations by looking at the phase, and we can determine what the X values of XM and RM. And so this is just a simple Excel spreadsheet, and you can see here that XM is 7 ohms and RM is about 22 ohms. And at that point, there is no slip. So the term in RL, the other components, is infinite. So there's no contribution to the circuit. Similarly, what we can do is we can then lock the motor down. So looking at this system here, what this does is it allows you to insert the induction motor into this cradle, and then you push that bar, which then prevents the induction motor from turning. So there's no rotation on the system at all. And when we do that, we lock it down, we go through the same process. The slip is 0. So because of that, there is this term in RL has gone to 0. And so the problem becomes identical to the problem of characterizing a transformer. And when we do that, we get these values here for the values you can see on the circuit diagram. There's the finished calculation. So these are the values of the resistors in the circuit. Those are the magnetizing components, again, much larger than these. And so that shows you how you characterize a three-phase induction motor. Now, what you do then is, once you've built your circuit model, it's a relatively straightforward task to put those numbers into a mathematical package like GNU Octave, and then to predict the speed torque curve that you're going to get out of an electrical machine. And we've done that here. If you want to get these files in GNU Octave and have a look at that yourself, then again, just ask Alistair and he'll provide that for you. And of course, the interesting thing is, as engineers, is what we want to do is be able to model a system and then to predict how that system is affected by any changes that we make. And what we tend to do is make some measurements, do a simulation, and then in an ideal world, the calculations that we've measured practically will marry up with the calculations that we make in a piece of software. But that's an ideal world. In practice, things are never quite that simple. So you can see a few curves here. The blue curve is our predicted performance of the induction motor. The yellow curve is the actual performance of the induction motor. And then, of course, you have to start to ask yourself, okay, why am I getting a difference? And there's lots of reasons why you might get some differences. There are mechanical losses in the system. There are some electrical losses in the system you haven't accounted for. So, for example, the drive chips, the wires, and other things like that. So there's always going to be a small difference between the ideal calculated result and the actual result. The third line here is we've actually had a go at doing some loss adjustment, but clearly we've done too much of it because it's too far away from the actual. But really the important thing is the blue and the yellow wires, lines, which are the predicted and the actual result. Okay, I think that concludes what I want to talk about today. Do we have any questions? What's the price of this, Alistair?
It would depend on who you're asking, I guess.
What's the customer price?
I think it's about £8,000 for the full set.
Does that include the locked rotor?
That doesn't include a locked rotor. I think it's about £600 for the locked rotor add-on. Okay. I'll get clarity on that. It's about 600. Any questions, guys? If you want to unmute yourself or put a question in the chat. Guys, any questions? Is now is the right time for questions? We've got maybe 5 minutes or so now where we can take any questions, whether it's about the electrical machines or the locked rotor add-on or the transformer add-on. I know some of the people that have signed up have already bought the electrical machines, but the locked rotor add-on and the transformer add-on are now available as well. So now if you've got any questions about these two, now's the right time, I guess. Just while I'm waiting for questions, I will just also let you know, for those that don't know, the lesson plans are available freely on our website. You don't have to make a purchase of the kit. You can go onto our website and have a look at them, even, you know, after this webinar. I will send you a link to the learning objectives and the lesson plans as well. But they're done in a really nice manner. They come as a PDF. You can print them off. You can put them on your VLE. You can do anything you want with them, essentially.
Okay, Chula. Hello, Chula. How are you? Nice to interact with you again. Are there any future editions of Electrical Machine System? We aren't planning any, and actually we've had some discussions about what we might do. What you often see in tender specifications is things like compound motors, and we've consciously taken a decision not to have that. It's interesting where people want some less utilized things like that. And we've taken a decision that compound motors won't be included because their usage in real life is small and diminishing. Whereas we've taken a decision that brushless motors definitely do want to be in there. We have had conversations about putting a stepper motor in there, and we've thought about that and discounted it for now. I suppose I'd like to push that one back at you and ask you what you'd like to see. We've also had some thoughts about how we might evolve the system in terms of accuracy. So we've thought about how we might give a better accuracy to all the instruments inside, but at the moment we don't have any plans to do that. So yeah, Chula, if you've got anything you want to see, then let me know. Okay, the locked rotor, can it be controlled remotely? No, it can't really. It's a very physical thing, so it's not possible to do that. But you're making me think now about how we might incorporate that with some kind of huge solenoid or something on the main sort of mechanics. I think the problem with that is it would always be coupled to the dynamometer, which provides a load, and so your results in the free running test wouldn't be as accurate. So I don't know. I'll have to think about that, but I suspect it's not practical.
Any more questions, guys?
Hi, Alistair.
Hi, Bill. You're right. How are you?
Not too bad. Not too bad. Thanks very much for this presentation. I think at the moment, and I'll have a discussion with yourself, Alistair, about it, is that the vast majority of our students that would be using this type of kit are distance learning at the moment, so they don't actually have access to the machine kit that we bought. So I'm not sure when we would have our students back. I'm particularly interested in the locked rotor mechanism, because I don't think we have that. We would need to add that.
Yeah.
Where are you from, Bill?
I'm in Scotland, Forth Valley College.
And which unit are you using this in? Which BTEC unit?
We use SQA HN, so it's an SQA Higher National Diploma, but we have one particular unit that we do at HN, which is electrical machine principles.
Okay.
most of the unit is, and its descriptor is very much kind of theoretically based, but I see opportunities for students learning the theory by practice, by using this kit. Yeah, absolutely.
Cheers, Bill. The actual electrical machines does have LAN capabilities now. I'm not sure if you bought an early one or not. It was something we added at some point. I'll have to check on your order, but you can actually control them over the over Wi-Fi, over Ethernet now, as a sort of distance learning tool. We do have a couple of slides on PDF that I can send you about how that might work for distance learning, but there is a bit of capability there, and I'll send you that. I'll make a note now, Bill, to send you exactly how you do that to control it over the Ethernet.
Good. Yeah. I'm back on campus this evening, so I can even just have a quick look and see whether we've got that capability in the.
Yeah, you'll see. All you have to do is look in the back of the controller, and you'll see where you can plug an Ethernet in straight away if it has that.
Okay.
So Bill, with your students, I'm guessing you do equivalent circuits then?
Yes, we do equivalent circuits. And
do you do a transformer and induction machine, or do you just do one or the other?
Yeah, no, we start off with transformers, and we develop the idea of the equivalent circuit, and then we in that unit we do DC motors, induction motor, squirrel cage, wound rotor, and then the last couple of outcomes is on synchronous machines.
Okay.
So yeah, we develop the equivalent circuit in the transformers, and then we take that over into induction machines.
And do you do anything about circuit characterization of synchronous machines or anything else, or is it just induction machines and transformers?
Off the top of my head, I think it's just the induction machines.
Yeah, we did do some work with a university locally, and they were doing equivalent circuits of the brushless motor, right? So that's another one you can do. We've kind of chosen not to get involved with that because we feel that most people will just do the transformers and the induction machines. But maybe at a good university, they want more practice, if you like. Yeah. And of course, the equivalent circuit of the DC machine we haven't covered, but that's very easy to do. It's only, I think it's just the back EMF, so it's actually quite straightforward, really. And you can do that with this, but we just haven't put that in the manual, you know.
We do touch on that in the DC machines, so that students can calculate speed and based on the back EMF characteristics of the motor. So we do touch on it, but we don't in that particular unit touch brushless.
Okay.
The other ones that I can think of is single phase motors.
Yeah.
We do single phase, split phase, capacitor start, shaded pole.
Yeah, we don't do shaded pole. That's another one, actually. They're quite common because they're dirt cheap little devices. People always talk about fans. There's probably millions of fans, but we don't have. It's not easy to get one in a nice chunky format that you can put onto this system. They tend to be all small little gadgets, don't they? Yeah, so it's not an easy one to incorporate, really.
Exactly. I think we have a couple of tiny ones that we just use to give the students an idea of this is what a shaded pole motor
looks like. Yeah, because they're weird little devices, aren't they, really?
Yeah.
And are you do you stop at equivalent circuits? You're not doing any modeling with Matlab or any other software package?
No, not at the moment, no.
Right.
Just a model, and they do some calculations, and that's about it.
There are some new BTEC higher nationals coming into force here in England, and they want you to do modeling with Matlab. And that's quite interesting because it's a whole nother step forward. And I think there's been a big drive to get the BTEC higher nationals to be much more university-like. And good luck to them, really.
Yeah,
that's a lot of work for someone, isn't it?
It is. The interesting thing is that they're currently redeveloping the SQA higher nationals.
Right.
across the board. They've got a project that they're calling HN Next Generation. So there's a pilot in electrical engineering meant to be happening later in this year, prototyping it for starting kind of pilot delivery next year. And it is moving much more towards a kind of project-based approach. So I can see things like machine principles, transformers, power systems becoming much more of an element of investigate and learn through investigation. Yeah.
Yeah. Good.
And I think this type of kit would be ideal for that.
Yeah, lovely. Well, hopefully you'll get your students back in the new year.
I hope so.
Get them using the kit. Yeah.
Yeah, missing them all.
Are you? Hey, there's not many lecturers who would say that.
Definitely, yeah. Miss a social interaction, Will.
Yeah, I bet you do actually. Yeah. Chula.
Hi, sorry, John, I could not say hi to you earlier.
Yeah.
So,
how's things with you?
I'm okay. Quite late in Colombo at the moment.
Oh, is it?
Yeah, it's about 8:15 now.
Yeah.
Switching between Future Talk and webinar.
Okay.
I hope everybody's okay in UK. I heard that you also locked down now, like we are now.
Yeah, we have. We've got one guy who's got it at the moment. David is our IT guy.
Okay.
And because he had it last week, Liam and Jane and one other person who came into contact with him have got to stay at home for a while.
All right.
And then of course there's all the engineers are at home, but we've still got about sort of 15 people here or something. So,
Okay.
but and actually we're managing really well. That's the interesting thing, is that everybody's still kind of up for beating it, and everything's fine, really. You know, it could have been a heck of a lot worse. So life's good, really.
Good.
And we're all a bit fed up, of course, because life's a bit on hold. But I bet that applies to all of us everywhere, doesn't it?
Absolutely. Yeah. I'll come back to the question that I asked you earlier, John, that you see in Sri Lanka, in some aspect, that we still hold on to some of the old technologies. You know, so even in the vocational training authorities, we still teach the carburetor as one of the technologies they have to learn, because it's still in use in many parts of in Asia. So they still use some of the old technologies when it comes to it, but we are in the process of changing it. That's why I don't want to commit anything to you right now. This might be a possible requirement, but then again, if the quantities are very small, it does not justify you to develop something new. So I also understand that. That's why I said I will get back to you with the possible requirement in the future on the basis of the development.
Yeah, there's lots of factors here. Another one is how we can source parts. Now, one of the reasons we're able to keep the costs low is that these motors are all custom made for us, but they're made within the sort of physical constraints of the tooling that the companies that we buy them from have. So if we wanted to do something quite different, the costs might be huge compared to what we've got at the moment. And so that's a consideration. Yeah. We certainly have the main ones. We have all the
yes.
We've got DC, we've got 3 types of DC motor, we've got 3 types of AC motor, and we've got the brushless. So there's enough there. And once you've done those, there's a diminishing return, if you like, in doing an 8th motor. I think that's what I tell people, and it's probably true, Chula, as well. So I'm happy with what we've got. I could be tempted to make a much higher power system. A lot of customers want to work on a 1 kilowatt system, and there's a great rationale for that. It's what you come across in industry. So why not work on something bigger? But then you're into a custom lab, you're into, you know, it's big, it's going to be a huge amount, you know, more expensive. And it's not really, Matrix has a kind of reputation for producing relatively low cost products, high functionality, things that can be stored easily and put away. So flexible lab space. So that's kind of not what we are really. And we're putting our energy into more things, which you'll see shortly. I'm just finishing off a load of process control stuff at the moment. Okay. So we've got 4 process control rigs that are going to come out in the next few weeks. And I'm at the stage now where getting these products to be finished is, you know, 5% of the work is hugely painful. Just getting everything right in the documentation, you know, it's not the interesting part of the project, but we're nearly there.
Good.
Okay, does anybody else have any more questions for us? Okay, I think we're done.
Okay, guys, just from myself and John, thank you for tuning in. Thank you for your questions. We'll send an email in an hour or so, and I hope you enjoy the rest of your day.
Okay, nice to see you. See you, Chula.
See you guys. See you, Bill.
Bye.
Bye.
Bye.